material in this class. So what is typically going to happen, not always, but very typically, is I'm going to give you some time to play around with stuff. There'll be equipment to use, motion carts that roll around that measure their own position and velocity, springs and masses and all sorts of stuff that you can play around with, and I will kind of point you in a direction. And that's what these preliminary labs are going to look like. Explore and experiment, take some measurements, see what you can figure out on your own. And I'm going to ask you to practice some skills while you do that I have never showed you. So some of you like that kind of thing. That's how you roll, and so that works really well for you. Others of you need me to show you how this stuff works at some point. And so that's what'll happen. We'll have a couple of days to play around, then I'm going to show you stuff. And then you'll have more time to work and develop and practice those skills. All right. So today we're going to go through some of the skills, in particular these first two that have to do with interpreting motion graphs. This last skill right here, converting a position versus time to a velocity versus time and vice versa, we'll start that today, but we won't get all the way through it. We'll just get partway through it, and then I'm going to give you time to work on some of those skills. The work that you'll do today, some of it is going to be stuff that I'm showing you. Some of it is still going to be things that I haven't showed you yet, but you'll get it. You'll get it on Thursday. So what I want to start with is this idea of interpreting motion graphs. And we've really only looked at two. There's a third one that we'll get to know a little bit starting next week, which is an acceleration versus time graph. But the ones that you were playing around with the motion sensors were position and velocity versus time graph. So let's start with a position versus time graph. And the first thing to think about here is that for a whole bunch of reasons, we generally refer to an object's position along a single line. It's one-dimensional, for those of you who know that. We give it the variable x. X is our location variable. T is our time variable. And that's not super complicated, except that when you set it up on a graph and graph it such that position is a function of time, then what you end up with is your x-axis is t and your y-axis is x. And that's unfortunate, because that's confusing. And it's even more confusing because, by convention, if we're dealing with horizontal motion, we call it the x variable, right? That's something moving along a line, sort of left to right or whatever, we think of that as x. X represents your position along that line. But if we know something is moving up and down, then we often usually call it y. So sometimes the y-axis for a position versus time graph is y, and sometimes it's x. When we start thinking about two-dimensional motion, one single object will have both a horizontal and a vertical position. So we'll have an x versus t and a y versus t, two graphs for the same object. One of those will have x for the y-axis, the other will have y for the y-axis. And it gets confusing pretty quickly. So just keep in mind that you are going to need to keep careful track in your brain of these things, and I'll try to speak really clearly when I refer to these things, talk about the x variable and the y-axis, and make sure that you know whether I'm talking about position or one of the axes on a graph, because the letters don't match up the way that we sort of wish that they would. And not universally, but typically, at least in this class, we're going to be measuring our position in meters. We'll be measuring our time in seconds. So it's always good to put units on things. For a graph like this, we're going to be thinking about it qualitatively. We're not going to need to have any numbers on here. We don't need any numbers to be able to think about an object's relative motion, its relative location, like is it further away from a certain place than it was before, which direction is it moving faster or slower. We can figure all that stuff out without putting any units on here at all. So I'm going to leave them off to start with. And this is from the preliminary lab. This was in there. These were the things that I was asking you in general to sort of give you a chance to think about those skills of interpreting a graph. The first one says, what does the slope of the position versus time graph look like when you're moving slowly versus moving quickly? And this is fun right off the bat because here's a line right there. Does that look like fast or slow motion to you? Anybody have a guess? Who doesn't mind having their voice show up on?
Slow.
Yeah, and so because it's not very steep, so we want this to be slow. And here's the thing. What is the definition of slow? Like if I tell you that I'm moving at 30 miles per hour, is that fast or slow?
Well,
Is it slow? It depends, doesn't it? If I'm in a car, not so fast. If I'm in a jet, you're not even off the ground. But if I'm in a little red wagon being pulled by a 7-year-old, that's fast, right? And so these are relative terms. So all we can say here is that it's not that this is slow, it's just that it is slower than, say, this. So if we have a steep slope, it's fast. If we have a shallow slope, it's slow. But it's not really slow, it's slower. And it's not really fast, it's faster. Compared to each other, these are relative speeds, right? The steeper the slope, the faster the speed. Is it fast? You would need to know what's moving and what the units are, right? So there's no universally accepted number that makes a speed fast. Fast for a baseball is very different from fast for a wiffle ball. All right, so the steepness of the slope tells you the speed of your motion. What about positive, negative, and zero slopes? Here are two sections where there's a positive slope. Here's a section here where there's a zero slope. And here's a section where there's a negative slope. What is the difference between these three sections? This section is positive, this section is zero, this section is negative. What would we see? What do those slopes tell us? Yeah?
You'd be going away from the point, then stopping, then going towards the point.
Right, so basically, the sign of the slope is an indication of direction. If the slope is zero, then our object isn't moving, it's motionless. If our slope is positive, then we're moving in one direction. If our slope is negative, then we're moving in the other direction. And this gets a little bit interesting too, for a couple of reasons. One is that so far, we've mostly been focused on trying to work with these sensors. And these sensors, come on in. Yeah, no worries. Yeah. Don't worry about it, it's all good. These sensors have some limitations. One of those limitations is they will only detect the position of something that is being faced by the little shiny circle. So if you're not like visible to this thing, your position doesn't get registered. Do you have a position? Yeah, I'm somewhere, right? It doesn't matter, this sensor isn't even plugged in, but I'm still somewhere. So when we look at these graphs, we have to make sure that we recognize that, like, well, if we make a graph with a motion sensor, there's going to be limitations. But if I look at this graph right here, there's no rule that says this graph had to have been made by a motion sensor. This has to reflect the motion of an object that's being tracked by a motion sensor that has the limitations that this one does. You all know about like air tags and stuff like that. Those are location sensors. Those can tell you where anything is at any time. Like you don't need this, and it can tell you just where you are. It uses a totally different system, but you don't need this to have a position. So what that means is a couple of things. The first is we can have a negative position. With the motion sensors, that would not be data that it could record, right? But it's absolutely possible for something to move past our position zero, whatever that is, and continue. So if I am walking toward this motion sensor and I just keep walking, right, I'm now in a position that the motion sensor would record as negative. It can't record it because it doesn't work that way, but you all could we could all agree that if I am right now standing at +1, +1 meter location, that now I'm standing at -1 meter location. We could agree. The sensor wouldn't show that. If we were using a computer and a graph, what would happen is it would start to glitch out right about here because it doesn't work very well for super close distances. And then as I moved away from it, it would be measuring like how far away the wall is. It wouldn't be giving us any meaningful data. But my position relative to this sensor is easy for us to see. So this is perfectly valid information. Where is position 0? We'll talk about that next week, but it's really like wherever you want it to be. Sometimes somebody else makes the decision. This sensor has it built in position 0, which is the shiny part. That is position 0 with the sensor. But if we were to go outside and go to the track, we could take a rock and put it down and say, this is position 0, and measure everything relative to that position. Positive would be one way, negative would be the other way. Is there any reason to say that positive is left or right or up or down or towards us or away from us? Not necessarily. We just need two directions. And one of them is going to be positive, one of them is going to be negative. The next section says, what does it mean when the slope is changing on a position versus time graph? So that would be something like this. What does it mean when instead of a horizontal line or a diagonal line, we have a line that is curved? And this one looks like it starts off with a negative slope and then it curves and becomes at least close to horizontal. What does that tell you? Yeah.
You're like accelerating or decelerating?
It tells you that's right. And what acceleration or deceleration means is that your velocity is changing. With these graphs, this is always going to indicate a change in speed. Okay, so a line with a constant slope is going to mean a constant speed. On a position versus time graph, when you see a curve like this, that's a change in speed. Steeper slopes mean faster, slower slopes, or shallower slopes mean slower. So what that means is we are starting here at a relatively steep slope, transitioning to a shallow slope. That's slowing down. This would be slowing down as well. We started off steep, we ended up shallow. A speeding up curve would look like this. We're starting off pretty shallow and getting steeper and steeper and steeper. Or this is a speeding up curve as well. So on a position versus time graph, we can see speeding up or slowing down. If the slope is getting more shallow, it's slowing down. If the slope is getting steeper, it's speeding up. And then the last thing here has to do with the coordinates of a point. And this is easy to show. It's a little hard to say in words. So basically what I mean is like this graph consists of a bunch of points that are infinitely close together, right? So this point right here would be a pair, right? And this would be a pair of coordinates. The first coordinate would be our x-axis, which is t. The second coordinate would be our y-axis, which is position, or x. This point right here tells us two pieces of information. Those pieces of information are the time of a measurement and the location or position of whatever object it is that we're measuring. Was this a sensor? Maybe. It might have been this motion sensor, but it also might have been us out on the track, or it might have been a car driving down the road, or it might have been anything that was moving. At some time, it had this position. And what that kind of leads you to, so that information can be useful. Like you might need to know in this class or in life in general, where was something at a certain time, right? And so that's what this information will give you. What's more interesting is when you start to think about it, well, so if position is a function of time, then if we kind of move our finger along the time axis and think about how our position is changing, we can tell the story of motion, right? Here we have an object that's located at a positive position. I don't know what it is, but I know it's on the positive side of our 0, wherever that is. As time goes by, it's moving and its position is becoming more and more positive. And now it's moving faster, got a steeper slope, it's moving farther in a certain amount of time. And now it's as far away as it's gonna get, and it's not moving. And then it starts moving the other direction. Towards the sensor? Well, if this were a sensor, then yeah, this is moving toward the sensor until it gets to here. But as it continues moving in that same direction, now it's moving away from the sensor. And again, there might not be a sensor, right? This might be you walking towards the rock on the track, and you just walk past it. Now, you're in positions that would be negative, and now your position is becoming more and more negative, but it's not happening as quickly. And now you're standing still. So you take your finger and you kind of move it along the graph and tell the story of how an object is moving over time, right? So that's what interpreting a position versus time graph looks like. Does anybody have any questions about that? Okay. The next one has to do with a velocity versus time graph. Velocity versus time graphs are a little bit more complicated, and the reason for that is because our brains, in general, have been trained to use a graph like this to show us where something is. We just, up until now, most of you have not spent a ton of time thinking about the speed and direction of an object's motion as it is reflected on a graph that shows velocity as a function of time. So it's going to be a new thing, all right? So what does it look like? What does motion look like with a perfectly horizontal slope? If we have motion like this, what would that look like? What would we see? If an object were moving with, and this were its velocity versus time graph. Any ideas what this looks like? Bastian?
That looks like just moving at a constant speed.
Right, okay, so we have the idea of constant, right? This section right here would be reflective of a constant speed. As time goes by, your speed doesn't change.
Yep.
You're not standing still. You're moving, you're just not speeding up or slowing down. What about this section right here? That also has a horizontal slope. What's happening here? Did you go back? You just went back to where you started, right? What do you think? Back to where you started? What's, yeah. So this is where, with a position versus time graph, 0 means a place. With a velocity versus time graph, this 0 is your speed. It's not that you moved somewhere different, it's that you stopped moving. Here, you're not moving at all. Okay. What about something like this? Or this? Here we have an angled line, right? It's a diagonal. And here we have a curved line. The slope is changing. What information is there? Forget about the fact that it's below the x-axis for a second. What does this straight line tell you about an object's motion? What does that look like? Yeah?
Motion is increasing.
Something is increasing. It's you're not, I'm not saying you're wrong, but there's a vocabulary thing there,
It's
yeah.
moving faster at a constant acceleration.
Yeah, it's moving faster. So, and we'll get into like, well, how do we tell if it's moving faster or slower? In this case, it's moving faster. And its speed is changing at a constant rate. That's what gives this line a constant slope. As time goes by, its speed kind of ticks up at the same rate. What about this? This is what? Any ideas? Philip?
Deceleration,
Deceleration? What does deceleration mean?
slowing down.
Slowing down, right? That's what we want this to be, Ryan.
You reach a plateau of speed and just.
You
keep
reach a
going.
plateau of speed. That's not the same as slowing down, is it? Yeah, when we see this, our brains want this to be slowing down. This looks so much like what we would expect slowing down to look like. But if you think about what the information on this graph is telling us, your speed is becoming more and more and more and more negative. Here, it's still becoming more and more negative. Here, it's not slowing down, it's maintaining a constant speed. That's what these horizontal lines mean. So this section right here, it's not slowing down. We need another way to talk about this. It's not that it's slowing down, it's that the rate of change is slowing down. It's speeding up, but it's speeding up less and less and less fast until it stops speeding up. That's what's going on here. And yeah, acceleration is the term that we use to refer to the rate of change of velocity. We'll talk more about that next week. Yeah.
Then what is negative velocity exactly?
Yeah, so let's talk about that because that's the next piece here. So let me just add that real quick. So this is changing speed, and this is right here the rate of change is changing. And that's a weird thing to talk about because that's like, well, you're not slowing down, but your speeding up is slowing down. Your speeding up is happening less and less quickly. Okay, and then the next piece here, what do positive and negative and zero slopes? Well, we figured out zero already. Zero means your speed isn't changing. If you're moving, you move at a constant speed, there's a zero slope. If you're not moving, you just persist in not moving. But positive, negative slope means something. A positive slope means that your speed is increasing in the positive direction. And we're gonna talk more, so I'm gonna defer like a detailed analysis of that until next week, because we still need to like define some terms and talk about like what does zero mean, what does slowing down mean, what does towards zero mean. We got some stuff that we need to iron out. But essentially, what these positive or negative slopes tell you is whether your speed is becoming more positive or more negative. That's really the limit of what we can say by knowing the slope. Now, in this case, we have a little bit more information. This is a negative slope, and we know that the speed was zero at the start. If your speed is zero, and then it gets more and more and more negative, then you're speeding up. You have to be. If you're moving in the negative direction, then you're gonna have a negative velocity. Negative velocity isn't something special, it's just what direction, right? If you have a negative velocity, you're going one way. If you have a positive velocity, you're moving the other way. If I were to use this little setup, this is my position zero, it's not a sensor, it's just a marker. If I say this is my positive direction and this is my negative direction, then 1 meter per second positive looks like this, and 1 meter per second negative looks like this. Same speed, different direction. I just walked by the sensor. I'm still moving in the negative direction now. The negative direction is this way. And I'm all the way over here now, and I can move toward the sensor in the positive direction. Still toward the sensor in the positive direction. Positive toward the sensor. Now I'm moving away from the sensor, still in the positive direction. So we can move toward or away from our 0 point without changing direction if we walk past it. So that, we have to iron all that stuff out, and we'll work on that next week. The last piece is this piece. We did this with the position versus time graph. This is the idea that if we look at a certain point that makes up any one of the infinite points on this graph, we can look at the coordinates. In this case, maybe that's 7 seconds and a negative 0.2 meters per second. We don't know because we don't have units on here, but the first coordinate is going to tell us the time of a measurement. The second coordinate is going to tell us the speed and the direction of whatever it is that we're looking at that time. That means we can talk about this object's motion the same way that we talked about a position versus time graph. Only what we're saying isn't how where the object is, but how fast it's going and what direction. So we can start here. At this time, the object is moving at a constant speed in the positive direction. So let's say positive is this way now, just because we can. So it's just moving, 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 and then it stops. And it stays motionless as some time goes by. And then it starts moving in the negative direction, slowly at first, and then faster and faster and faster and faster, and then it continues to speed up, but it doesn't speed up as quickly, and eventually it's moving at a constant speed. I can't show you that because I can't keep moving and point at this thing at the same time. Like, I ran out of room, right? But the position of this object is somewhat predictable. We know it's going to be moving this way for a while at a constant speed, and then it's going to stop, it's just going to stay put. Then it's going to start moving back, slowly at first, speed up, speed up, speed up, speed up, speed up, speed up, but speeding up slower, and now constant speed. Eventually it's going to go past its original position and keep going, right? If this just extends on, we don't know what happens, but it might just keep moving at a constant speed this way. So that would be like you throw a boomerang and it goes off this way for a while, and then it stops and it hovers for a little bit, and then it slowly starts to come back, and then it speeds up and goes faster and faster until it sort of hits a maximum speed, and it just keeps going. That's what that would look like. So those are skills that I want you all to be able to do. And what I want to show you next, so there's a couple of things that I'm going to defer to Thursday. So this is one of them. The first thing is we're going to work on this on Thursday a little bit, and basically this is like a graphic organizer for interpreting these motion graphs. We can think about the motion graphs in terms of what does a single point tell us, and what does the trend tell us? The trend is the slope of a line or a curve, the positive or negativeness of it, the steepness of it, right? And we can think about that for a position versus time graph or a velocity versus time graph. We're going to think about it very superficially for acceleration versus time as well, but not yet, okay? But we'll hit this on Thursday. We'll come back to this on Thursday. And what I want to show you today is a skill that I think some of you probably made a little bit of progress on in the Match This Motion preliminary lab, but most of you didn't get here, or if you did get here, you weren't quite sure how to go about doing it. So I'm going to show you how to do it. And basically what we can do is, if we think about the fact that a position versus time graph tells us something about how fast something is moving and in what direction, steeper slopes mean increasing speed. So we have an idea of whether something is going slower or faster by the steepness of the slope. And the sign of the slope tells us direction. Positive slopes are moving one way, negative slopes are moving the other way. We could use that to create a velocity versus time graph. If we know how fast something is going and we know what direction it's going, then we can talk about how its velocity looks over time. So I'm going to walk you through an algorithm. An algorithm is a system, a series of steps for accomplishing a task. Here's the algorithm that I use to create a velocity versus time graph from a position versus time graph. The first thing that I do is I look at my position versus time graph and I break it into chunks that all have the same slope. So when I look at this position versus time graph, I see that for the first, you may not be able to read these units, and that's okay. This is 2 seconds here. For the first 2 seconds, I have a constant slope here. For the next 2 seconds, I have a constant slope here. For the next, this is 1.5 seconds. I have a constant slope. And then there's a 0.5 second here where there's a constant slope. There's 2 seconds here of a constant slope. This is 1 second with a constant slope, and then 2 seconds with a constant slope, right? And those are all like, we can think of those each as being like line segments. They're straight lines, constant slope, and we can find the slope because we know how to do that. It's rise over run. For the flat sections, the rise is 0. So we know, like, rise over run is 0. If your rise is 0, doesn't matter how much time you're there, you have a slope of 0. So for the first 2 seconds, we have a slope of 0. From second 4 to 5.5, we have a slope of 0. From second 6 to second 8, we have a slope of 0. The rest of these time periods, it's not a 0 slope. For times 2 to 4, it drops down by 10, and again, you may not be able to read this, but this is 0, 5, and 10 meters. So it goes from 10 to 0. That is a rise of negative 10. That happens over 2 seconds, so that is a slope of negative 5. From 5.5 to 6 seconds, I'm going from position 0 to position negative 15. That's a rise of negative 15. Negative 15 divided by 1/2, which is the run, is negative 30. So the slope here for this section is negative 30.